So have you noticed the alarming surge in satellite malfunctions recently, specifically over the South Atlantic? If you are a mission planner, an aerospace engineer, or really anyone managing orbital hardware right now, you absolutely have. It is, without a doubt, one of the most pressing operational risks in low Earth orbit today. But what if I told you that the root cause of these orbital hazards isn't just coming down from the sun, but is actually being driven from literally 3,000 miles beneath our feet?
Welcome to this explainer. Think of me as your lead geophysicist today. We're going to completely unpack the planetary mechanics that are driving these radiation risks. We'll be connecting the dots from the absolute deepest parts of Earth's core all the way up to the magnosphere. It is a wildly fascinating look at exactly how deep Earth dynamics create deep space hazards.
Okay, here is our mission briefing roadmap for today. First, the South Atlantic Anomaly. Second, decoding deep core seismology. Third, core and mantle dynamics. Fourth, navigating magnetic pole shifts. And fifth, solar storms and seismic triggers.
Let's dive right into Section 1, the South Atlantic Anomaly.
Basically, the South Atlantic Anomaly is this vast, expanding weak spot in Earth's protective magnetic shield. Geographically, it's located southeast of South America and Africa. Now, for those of you actively managing orbiting hardware, you know that passing through this specific zone exposes satellites to highly elevated cosmic radiation, and that directly increases the risk of some critical malfunctions. We're talking single-event upsets, bit flips in memory, and severe long-term hardware degradation.
And here is the kicker, plus 50%. Recent data from the European Space Agency's swarm satellites shows that this anomaly has actually grown by an area nearly half the size of continental Europe just since 2014. So if you're running mission risk models based on data from even a decade ago, you are completely flying blind. This anomaly isn't just sitting there, it is actively and rapidly expanding.
Moving down into Section 2, Decoding Deep Core Seismology. Since we obviously can't just drill a hole 3,000 miles into the core, researchers use a pretty brilliant step-by-step methodology relying on seismic data to map out the deep Earth. First, they record repeating earthquakes, like the 121 distinct events recorded near the South Sandwich Islands. Second, they analyze the seismic waveform differentials from these quakes as they echo through the planet. And third, by tracking these temporal changes over decades, they can virtually map out inner core shifts and precisely measure its rotation speed. It's like taking an ultrasound of the planet. And this kind of seismic geodynamic analysis reveals some intense structural deformation deep underground. Specifically, researchers found a massive slab of the Pacific Plate that literally sank 660 kilometers down into the mantle. By studying these incredibly deep focus earthquakes, we can actually reconstruct the complex thermal and physical environment deep within the Earth. It really just goes to show that the deep Earth is incredibly dynamic and shifting.
And when we compare these localized seismic readings, it reveals even more. By analyzing short-distance variations in earthquake locations against our baseline parameters, scientists can detect spatial changes in seismic radiation efficiency. They can actually trace viscous deformation happening right near the inner core's surface. It proves that the core is absolutely not just a perfect, uniform, solid sphere down there. It deforms, it shifts, and it reacts. So, let's look at the timeline of these core speed changes. Back in 1971, Soviet nuclear tests provided our initial baseline seismic data. By 1991, we started collecting targeted data from those South Sandwich Island quakes. But the really critical pivot happened in 2010. That is when the inner core actually began to backtrack. It literally started moving slower than the Earth's surface. And by 2023, this massive slowdown trend was unambiguously confirmed. The engine of our planet is basically shifting gears.
Which brings us to Section 3, Core and Mantle Dynamics.
So why is the inner core slowing down? Well, it's heavily influenced by gravitational tugs from dense, rocky regions in the overlying mantle. And we actually know these structures exist because we can detect rare primordial helium isotopes leaking straight up from the core. These ancient helium leaks prove the Earth formed inside a solar nebula, and they were likely released when early cosmic impacts completely remelted the crust billions of years ago. Today, massive superheated rock formations beneath Africa and the Pacific cause the churning liquid iron of the outer core to stagnate. This stagnation creates what we call reverse flux patches at the boundary, where magnetic field lines unexpectedly pull back into the core. And that right there is exactly what drives the intense South Atlantic anomaly.
Okay, let's look at Section 4, Navigating Magnetic Pole Shifts.
The changes happening to our magnetic field are definitely not evenly distributed. For example, over Canada, the strong magnetic field region is rapidly shrinking. It's weakened by about 0.65% of Earth's surface area. To put that in perspective, that is roughly the size of India. But meanwhile, over Siberia, the strong field region is actively intensifying and expanding by an area comparable to the size of Greenland.
And this leads to a very practical reality for all of us. The gradual movement of the northern magnetic pole towards Siberia directly impacts global navigation and satellite tracking systems. If you're a mission planner, this is exactly why you have to constantly adjust your global tracking architectures. The magnetic map of our planet isn't static, it's a living, breathing, shifting thing.
Finally, we reach Section 5, Solar Storms and Seismic Triggers.
Now I want to introduce you to a groundbreaking concept known as the Kyoto Capacitive Coupling Model. Think of the Earth's ionosphere and its crust as two highly charged metal plates, with the neutral atmosphere in between acting as an insulator. It's basically a giant planetary capacitor. When a moderate G2 geomagnetic storm hits Earth's magnetosphere, it radically alters that electrical balance. Intense electric fields actually propagate down through the atmosphere and into microscopic voids within fractured, water-saturated crustal rock. The resulting electrostatic pressure from this can actually trigger an earthquake. In fact, just 36 hours after a recent solar storm, a billion-year-old fault near Uluru in Australia snapped. The sun literally reached through the atmosphere and moved ancient rock.
As Professor Chris Finley from the Technical University of Denmark points out, the South Atlantic Anomaly is not just a single block. There's something special happening in this region that is causing the field to weaken in a more intense way. So for all you mission planners out there relying on swarm satellite data, the big takeaway is clear. You absolutely must remain vigilant. These anomalous regions are actively shifting and evolving way faster than we ever anticipated. Which leaves us with a final, pretty provocative thought. We know the Earth's inner core is slowing down, which alters our magnetic shield. We know this creates severe radiation hazards for orbiting satellites in the South Atlantic. But if space weather can reach completely through that weakening shield, with enough electrostatic pressure to trigger deep crustal earthquakes, are our satellites really the only systems at risk? I think it's time we start seriously rethinking the profound, interconnected vulnerabilities between deep Earth geology and deep space operations. Thanks so much for joining me on this explainer, and definitely keep your eyes on the data.